Good day, everyone. So today we're going to go over section 10.2, part 1, and we're going to actually create a confidence interval for the population portion P. So we're going to go through two examples with regards. In 2020, a random sample of 100 adult Americans was taken. They were asked if they would be willing to pay much higher prices to protect the environment. The sample found 80 adult Americans that would pay more. Find and interpret a 95% confidence interval for the proportion, or we could have said percentage, of all adult Americans willing to pay much higher prices to protect the environment. So you could have said either one, percentage or proportion. So clearly, it states in the problem, find and interpret 95% confidence interval for some sort of percentage or proportion. Okay? All right, so what's the underlying variable? What are we collecting data with regards to? Well, if somebody came up to you and said, hey, are you willing to pay more, much more higher prices to protect the environment? Either you're going to answer what? Yes or no. So the variable that we collect the data for is categorical. Categorical. And since the variable is categorical, we get to analyze this with a proportion or a percentage. All right, what was the sample? 100 adult Americans up here. It's a random sample of 100 adult Americans. That means the population is what? All adult Americans. Our sample size N is obviously 100 because there was our sample. How many people did we ask? What would be a success? Finding a person that is willing to pay more to protect the environment. Remember, success is not either good or bad. It's just how the problem is defined. And we're trying to find a 95% confidence interval for a proportion that is willing to pay higher prices. That means every time we find a person like that, success. How many successes did we have? We had 80. That's X. That's X in the problem. So the sample proportion, which is equal to P hat, is 80 over 100 or 0.8. So we had 80% or 0.8 of our sample that said, yep, willing to pay higher prices to protect the environment. But we know P hat is not going to match the population proportion P exactly, but it's going to be close. So what are we going to do? We're going to start with P hat, and we're going to create the confidence interval around it. All right. So for every inferential technique, there are conditions or slash assumptions in order to use a certain formula. So every time we go through a different inferential technique, we're going to have to go over these conditions, possibly assumptions, all right? So either we need to take a random sample or the data came from an experiment. Remember, experiments are randomized, all right? And so we need some randomization going on here. Then two, we need to confirm the central limit theorem. So if we knew P, that's the key here. If we knew P, all right? So if we knew P and n times P was greater than or equal to 10 and n times 1 minus P was greater than or equal to 10, the central limit theorem applies. Remember that from the last chapter? Well, okay, however, we don't know P, right? That's the reason why we're creating the confidence interval. So when we don't know P, what are we using in its place? P hat, right? P hat. So for a confidence interval for the population portion P, we need to show that n times P hat is greater than or equal to 10 and n times 1 minus P hat is greater than or equal to 10. If we show that, then the central limit theorem applies. So I want to show you a couple of things here. So let's focus on the first part here, n times P hat. All right, so let me remind you of something, is that P hat is equal to X over N. All right, we knew that. Well, let's go ahead and multiply both sides by N. All right, and what's going to happen on the right-hand side of the equation, what's going to happen to these N's right here? They're going to cross out. So notice here that once you cross them out, what do we get? We get N times P hat is equal to simply X, the number of successes, right? And so so this right here, this shortens down to just simply X, okay? So if the number of successes, which is equal to X, which is also equal to N times P hat, is greater than or equal to 10, then we got the first half of the central limit theorem going, right? Well, let's focus in on the second part right here. Well, what we're going to do is we're going to distribute the N through the parentheses. Distribute the N through the parentheses. So what you would end up with is N minus N times P hat. Well, what did we just find out that N times P hat was equal to? We know that that's equal to X. So, and that's the number of successes. So we substitute X for N times P hat. And what are we left with? We're left with N minus X. Make sense? All right. So we know that N times P hat is equal to x. So we have n minus x, right? And the c. So if we took our sample size minus the number of successes, what is n minus x then? That's the number of failures. So what we just found out is that as long as the number of failures, which is n minus x, is greater than or equal to 10, then we have the second part of the central limit theorem. Sort of makes it a lot quicker than doing the multiplication. Okay, you just look up the number of successes, do a little subtracting with n. You got the number of failures. If they're both greater than or equal to 10, hey, central limit theorem applies. We're good to go. Right? So all we got to do is show both of these. All right, and then the central limit theorem applies. And if the central limit theorem applies, that means the probability distribution will be approximately normal. We can use our z here, okay? And we can use our formula that I've been showing you. All right, so in our problem here, we're creating a 95% confidence interval. If you want to go back and take a look at that, remember I told you that's going to be stated directly in the problem. That means we're going to be using 1.96 for our critical value. So I think we have everything that we need then to do our calculations here. So let's see. We took our random sample, check. We checked onto this, right? We got 80. Let's see. We got number of failures is 20. That's greater than or equal to 10. Check mark, right? Since both are true, the central limit theorem implies and the sampling distribution of p hat is approximately normal. Hey, we can use the formula that we've been using. If I went too fast there, maybe go back and take a look there. But it's kind of straightforward when you think of it in terms of x and n minus x, number of successes, number of failures. So I think we have everything that we need then. So we got a p hat of 0.8. We got our critical value 1.96. We put that stuff into the formula. I'm going to assume that you can do all this in your calculator. If you have any problems with your calculator, you can always give me a we can always do a WebEx, but I'm going to think that most people can do this in their calculator. And so I came up with 0.04 for the standard error, 1.96 for the critical value, 0.8 for the point estimate. When I multiplied 1.96 times 0.04, I got 0.0786. Excuse me, 0.0784. Sorry about that. And that is the margin of error. So we have to apply the margin of error to the point estimate. So I did that there. And we get the lower and the upper bound of the confidence interval. And so what do we think is located between these two numbers? We think that the population proportion, sorry, my had a little screw there. There we go. Get rid of that. What do we think is located in there? The population portion P. So we think P is located somewhere between like 72.16% and 87.84%. We don't know exactly where, but we're pretty sure it's located between those 2 points. All right. Final step would be to interpret the confidence interval. So the first step was to verify the conditions. We did that. Second one is to calculate the confidence interval. We did that. The last step is to tell everybody what you just did, right? So let's go ahead and do that. And what we're going to do is we're going to start with, we are 95% confident that, and so if we were creating a 99% confidence interval, we would say we're 99% confident that, all right? But here it was 95. That, before we get any further, what exactly does this mean? This is important. A lot of students do not understand what this means. So let's slow this one down just a little bit. What does this mean? Well, first, this statement, believe it or not, has nothing to do with the individual confidence interval, this part of the statement, all right? This really has very little to do with our individual confidence interval, okay? What it means is this, is that if we consider all possible samples of the same size and create a confidence interval for each one of them, 95% of all the confidence intervals will include the parameter, will basically do its job, okay, and 5% will not. So 95% will capture the true population proportion P, and 5% will not. That's what it means to create a 95% confidence interval. So basically, 19 out of 20 of all possible confidence intervals will include the parameter if you're creating a 95% confidence interval. That also means basically 1 out of 20 will not include the parameter. So what we're hoping then is that as researchers, that we don't run into bad luck. When does this happen? When do we capture it? You know, when do we get one of the confidence intervals that actually does its job? Well, by chance, right? We're playing the odds here. We're playing the odds. We're counting on the fact that 95% of all possible confidence intervals will contain the parameter and 5% will not, and that the one that we created is one of the 95 percenters. It's as simple as that. It's as simple as that. We're playing the odds as researchers. So we don't have to go ahead and look at an entire population and take a census. Okay? We're willing to play these odds here, willing to play the game, as long as we get to take a sample instead of looking at an entire population. All right? That's the game that researchers play. Okay? All right, let's move on. You might want to make sure that you understand that one. So we're going to start this off with we are 95% confident that the proportion, right, of all adult Americans that are willing to pay much higher prices to protect the environment. So in other words, if you really think about it, what we're saying is that we're 95% confident that P, the population proportion P, the proportion of all, we're not making a confidence interval for the sample of 100 adult Americans. We know what happened with our sample, all right? That's not what we're making a confidence interval for. We're making a confidence interval for the entire population. So notice it's for all adult Americans, for the population. And so really this part that started with the proportion and ended with the environment, all that is saying we're 95% confident that P, and this is how P is being defined in the problem. Okay, that's the parameter that we defined in the problem. And this will be stated usually right in the problem. Okay, notice right here it says find and interpret a 95% confidence interval for what? For the proportion of all adult Americans willing to pay a much higher price to protect the environment. So usually it's got to be stated kind of in the problem. If we want you to make a confidence interval for a parameter, we got to tell you what the parameter is, right? So it's a lot of times it's just stated right in the problem. So finally, to end this, is what is between the two values, right? The two values here. So I put proportion here, and since I put a proportion, I'm going to put this as decimals. All right. If I said we are 95% confident that the percentage, then I would go ahead and change these to percentage. All right. And there you go. All right. A little harder than that. All right. Want to try the second one? So a large university is concerned about the percentage of its students that have COVID-19 but are not exhibiting any symptoms, meaning they're asymptomatic. The university randomly samples 1,000 of its students that aren't exhibiting any symptoms, and 19 are shown to have the virus. Construct the 99% confidence interval for the percentage of all students at this university that has the virus but is asymptomatic. So probably this is a little far-fetched. I doubt that a university is going to test 1,000 of its students. However, I know that Bowling Green this year, my son goes there currently, and Bowling Green was testing students every week randomly, all right, to see if they had COVID, see if they were exhibiting any asymptomatic symptoms. I mean, they were asymptomatic, but they exhibiting no symptoms, excuse me. So they had it. And so, but I made it 1,000. So what? I just made up a number. With regards to this, probably they created a 95% confidence interval. That's what most studies do. Here, I wanted to change it around, so it's 99. All right. So what's our sample? Our 1,000 randomly selected students, our population, all students at this university. What's the underlying variable? Well, the student is asymptomatic. Yes, no, categorical. Because it's categorical, we're going to analyze this with the percentage or proportion. What would be a success? Remember, it's not anything good or bad. It's finding an asymptomatic student. How many did we have out of the 1,000? We had 19. So p hat, our sample proportion, is pretty low, right? It's pretty low. It's 0.019. 0.019. All right. Verify the conditions. Random sample. We did that. Check mark. Right? Check. 2. The number of successes is equal to 19. That's greater than or equal to 10. Check mark. Number of failures. Pretty big number. Greater than 10. Greater than or equal to 10. Check mark. That means that since both apply, essential limit theorem is good, and the sampling distribution of p hat is approximately normal. Time to calculate our formula. There's our formula that we're going to use. We throw in all the numbers. Remember, we're creating a 99% confidence interval. That means our critical value is 2.58. And that's what I got for the margin of error. It's 0.0111. So I'll apply that to the point estimate. And I got here 0.0079 to 0.0301. So we are 99% confident that the percentage of all students at the university that are asymptomatic regarding COVID-19 is between 0.79% and 3.1%. So the university now has a pretty good idea of what's going on campus with regards to asymptomatic students, percent-wise, and also they probably have a pretty good idea of the percentage of students that have COVID and are exhibiting symptoms. So they have a pretty good idea of the percentage for the entire population that actually has COVID then. All right, that takes us to the end of this section. Thank you for your time.